Hey, word up my peeps, it's still summertime for me, but we're at some point in the year. I don't know exactly what week, but we're there. So let's look at chapter 6b. Again, if you haven't watched the video for 6a or you haven't had it in class, go back to 6a. Alright, so we're going to look at the types of bonds. Now, in covalent bonding, we do have bonding pairs, and there is something called the electrostatic force. There's positive and negative charges in atoms that attract or repel each other. Now, we do have, for bonding pairs, for example, atoms that are the same, and they are called diatomic elements, like H2, N2, O2, F2, Cl2, Br2, and I2. Those are all examples of the diatomic elements. So this is where we start talking a little bit about the Lewis dot structures. Gilbert Lewis is the guy who came up with it, and that's a picture of him there. And it was a way for any science student to be able to make a notation as far as how do the atoms arrange themselves, what kind of bonds can they do? Are we talking, do they share just one pair of electrons, or two pairs, three pairs? What's going on with that? And this is the notation for covalent bonds. Now, we really can't use this necessarily for ionic bonding. It's a little bit different. But this is what we have. And as you can see, again, on the group 1, lithium, sodium, potassium, one dot, one valence electron. We go to group 17, fluorine and chlorine and bromine and iodine. They have their 7. Yeah. So that's the dot notation, or Lewis structure, where they share electrons. The general idea. All right. So example number 1, we can look at chlorine 2, and here's another picture of Lewis here. So here's 2 chlorines. They each have 7 electrons, and we can arrange them that it will look like this. And that would be correct, because you got 2 chlorines in the 2 electrons between the 2 chlorines. And then here, this forms what we call a single bond, because there's pairs of atoms between between atoms. Now it's getting a little late in the day. Okay. We can do the same thing for hydrogen as well. Hydrogen has 1 valence electron. Put them together, and here you go. Here's hydrogen, or H2. We can represent it this way. We can also represent it this way. But when we start working with bigger molecules, we're going to be using this, not so much this. Okay? Here we go for water. So here's hydrogen blue, hydrogen red. Here's our oxygen with its 6 electrons. And we can hook them up that ultimately oxygen has its 8 electrons, right? And hydrogen has 2 because that's the most it can take. You'd say, well, why can't hydrogen take 8? That's because it's the annoying little kid who can only take 2 electrons at most. That's it. End of story. Deal with it. All right. Now here we have diatomic oxygen. Now the main goal here, when we do move these dots around, is finding out, hey, each atom wants to have 8 electrons. Now there are some exceptions, like hydrogen, for example, that the most they can have is 2. But most of the atoms out there want to have 8 for covalent bonding. So here's our 1 oxygen, here's our other oxygen. So you can see here that there are not 2 electrons, but 4. So 2 pairs of electrons hooking up. And what does that mean? Well, if you cover this oxygen up, you got 1, 2, 3, 4, 5, 6, 7, 8 electrons around this oxygen. Octet rule satisfied. If we cover this side here, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons on this side here, and the oxygen is fulfilling the octet rule. So these 2 oxygen atoms are sharing a total of 4 electrons, or 2 electron pairs. Now we represent that with 2 lines like this, one to represent the red, one to represent the blue, and this is what we refer to as the double bond. Okay? Now, this goes into the instructions about how to create the Lewis structure. And again, Lewis structures really are made up only of covalent bonds. For what we are doing here in Gen Chem, electrons are shared between atoms when a non-metal atom bonds with another, or two identical non-metal atoms bond. So single bonds, two electrons shared between atoms, we just looked at it for the hydrogen. Double and triple bonds. So double, you just saw it a moment ago. Two pairs of electrons are shared between atoms, like carbon dioxide, right here. That's a pretty common one. Triple bonds, you don't see them that much compared to double or single bonds. The most common would be single bonds, but then you get double bonds. You do have triple bonds. That's the highest you can go. Three pairs of electrons are shared between atoms, like N2. And then carbon monoxide, quite poisonous to us. The N2, this makes up most of the air that we breathe. So the more bonds you have, the tighter the hookup between the atoms themselves. So it's probably kind of an important thing for this to have a really tight hookup, and that would allow life to survive on the planet. Go figure. Now, moving on. There are molecules out there that they also hook up. And this is where we get into polyatomic. Poly meaning many, atomic meaning atoms. So many atom molecules have one or more central atoms bonded to surrounding atoms. Now, so when we look at a molecule, we can go and look at, hey, this here's PCl3, phosphorus trichloride. So you got phosphorus here in the middle, and then you got the chlorines out on the edges there, like that. And you can see Lewis dot structure-wise how we did it. Here's water. Everybody and their mom should know about the water. Everybody and their mom should know about CO2 at this point. Now, what about ethane or ethylene? Now, if you notice, they're made up of the same basic parts, carbon and hydrogen. Here, though, you've got a single bond between the carbons. You got 6 hydrogens. Now, ethylene, on the other hand, you've got a double bond between the carbons, and then you have 4 hydrogens, not 6. Then you have acetylene, right here where you have a triple bond between the carbon atoms and just 1 hydrogen atom on each side. Acetylene, think about acetylene torches that they can use for welding. Now, here's the deal. Hydrogen cannot be ever the central atom in a molecule. Well, why? Because it's the annoying little kid. It's tiny. You can't do anything with it. It's along for the ride. Okay? Something to think about. Now, is there a way to predict valence electrons? Yeah, there is. Okay? So how can we predict the number of valence electrons? Well, all nonmetals, except hydrogen, can be predicted by the following formula. The valence electrons is equal to the group number that your thing is in, your element is in, minus 10. That's a very quick, easy way. Okay? The number of valence electrons. Now, how can we predict the number of covalent bonds where nonmetals are bonded, are involved? Formula, covalent bonds equals 8 minus the number of valence electrons. Okay? So it's a quick, easy formula on that. Steps for drawing the Lewis structure. Okay? Really quick, we're going to spend time in class working on this. So it's a fairly straightforward thing. Okay? And that just continues going through. It's just in words what we're going to be doing in class. Okay, now we got to talk about, we talked about polyatomic molecules. Now we're going to look at polyatomic ions. What are they? Well, again, it's a group of atoms that you have a total charge. It's either going to be positive or negative. And the charge tells us how many electrons in the group loses or gains. So if you got NH4 with a +1 charge, that means did they lose an electron or did they gain an electron? We know that it's not 0 because it says it's a +1. Well, that means that it lost an electron. That's how come it went from a 0 to a +1. Okay? Usually the polyatomic ions are anions. They have a negative charge. Not 100% of the time. Sometimes they are the cations, the positive charge, remember? Right? Polyatomic ions often act as a unit, and they'll stay together during reactions, which is kind of interesting because they're so tightly bonded that way. Well, let's take a look. What are their charges to fill? Why are their charges? Again, it's filling the valence shell of each atom in the polyatomic ion. So here we have our atoms here, cations and anions. Here are our polyatomic cation and anions, and you can see that we have differences in there, okay? So we could combine any of these with any of these, and we can make a chemical out of it. We can have a chemical formula for it. Now, it doesn't say whether it's stable or whatnot. That's another issue. Then we get in, so that's it for covalent bonding. Now we're going to take a look at, well, I think I'm going to stop here because this is going to get a little bit more involved. All right, I am going to stop here, but now you know about covalent bonding, now you know about nonpolar and polar covalent, and you know how to do Lewis dot structures. All right, take care.